start with the lecture then. We're talking about the Fourier transform, or we just talked about the Fourier transform, right? And we're about to introduce the discrete Fourier transform. So let's do that. Obviously, I'm just going to be using Dct as the typical abbreviation that you're familiar with for discrete Fourier transform. So what's that? Oh my gosh. I'm going to talk about DCTs too, but thank you. But yeah. No, that's how we call it, DCT, just to confuse people. Okay, DFT. So the DFT is exactly the same that we derived for the Fourier transform, right? Remember that we had our synthesis and our analysis, exactly the same thing, but now it's in the discrete domain. So in particular, we are going to use a finite number of Fourier bases, right? Or FCs. So what I'm going to do is I'm going to take the Fourier basis, which was n omega n that I had, and I'm going to say n goes from 0 to, say, capital N minus 1. Or, I say this is n bases, so I'm going from 0 to n minus 1. And I don't know if I used W or omega before, but either one. Okay. Omega, it's the most classical one. Omega n, remember, it's equal to 2 pi over t times n, right? So that means that we can now rewrite our synthesis as the sum of this limited or finite basis set, m from 0 to n minus 1 of 2 pi over t f of omega sub m times the exponential function, as always, I omega mt. And let's see. And it is common to give this notation that we used earlier. T sub n is equal to n t over capital N, which yields that other notation that you will see. You may see this one, but I think most commonly you'll see this other one, which is the sum from 0 through n minus 1 of 2 pi over t of f omega m, the exponential function, I omega m tn, right? And repeating the same argument as before, we get the analysis f m omega m, is equal to t over 2 capital N pi, the sum from 0 to n minus 1 of f Tn, the exponential, now the inverse, because I'm going back, so negative I omega m Tn, right? Now, this can also be generalized to multiple functions. So in that case, I'm going to have f of m, where f is bolded now, or you can add an arrow to indicate that this is a vector of functions now. Okay. And the same thing for capital F. And the same applies. So now I'm going to have that my f of m is equal to these fn's summed over from 0 to n minus 1 times the exponential of I mn 2 pi over capital N, and capital F of n, it's 1 over capital N, the sum from 0 to n minus 1 of f, that should be vector, obviously. Now, f m, and the exponential function now negative of m n 2 pi over n, right? Same thing, but for a function of functions, right? As we have derived here before. Now, a very popular basis set that people use in a variety of image processing, computer vision, machine learning, and other applications is the discrete cosine transform, the Dct basis. That's, for example, used in JPEG, MP3s, MPEG, and the like. Now recall that the Fourier basis uses the cosine and the sine waves, right? Written as a complex number, right? So to think about this, e to the power of I pi, for example, or I pi half, it's a 90-degree rotation, right? And pi, it's 180 and so on, right? Pi over fourth, it's 45 degrees and so on. So you can think about this, and we'll talk more about this in our next lecture, I guess, but you can think about all these different concepts that we have been talking about as the hypersphere, right? So in 2 dimensions, there would be the circle, S1. In 3 dimensions, it would be S2, the sphere. And in more dimensions, it would be a hypersphere of SP minus 1 dimensions, where P is the dimensionality of your space, right? Now, I would have to say that the sphere, hypersphere in general, is probably, not only historically, but probably the most important topological object you'll ever encounter. Okay? By topological object, I mean the object itself, right? If you know anything about topology, topology is the area that's concerned with shape and shapes that you can deform as much as you want, right? So a sphere in topology, you can deform it by flattening it. You can do anything that you want except take a pair of scissors and cut it, right? You can never cut, but you can deform it as much as you want. The sphere, both in geometry, in topology, in certainly algebraic topology, is the most important, I think, object that you're ever going to encounter. And as we have seen already in this class, it has a very large number of applications. And as I'll mention in my next lecture, you'll see it appeared again when we introduce the idea of the projective space yet again. But in that case, when we have this rotations e to the power of I something, some angle, right? That just defines the rotation on the sphere, right? But if I have a, say, 45-degree angle here, right? I can also define this by computing here the cosine, right? And the sine, right? So what this gives me is this coordinate, and the cosine gives me that coordinate. So I can also describe, right? And I'll go over this again in the next lecture. We can also define the sphere itself. Can be defined, every point in the sphere can be defined as the cosine and the sine, right? Vector. So we can actually decompose this that we have done here as a sum of cosines and sines, right? It's a polynomial of cosines and sines. But in fact, the cosines, we can prove that. I'm sure that if you take signal processing, they prove that. You can prove that the cosines can span the whole space too, right? Not the sines, but the cosines. So the cosines are very typically used as a basis set to represent your space as well. And again, hold until next lecture to fully understand why the sphere represents a whole space, right? And believe me, it does. The sphere represents the whole space. That's the beauty about the projective space, right? And we'll talk about this. If we have time, I don't think we'll have time, we could talk about Quaternions, which is really cool when you go to 4 dimensions, because in 1 dimension, we understand geometry in 1, 2, and 3 dimensions, right? Because we're used to it. But once you go to 4 dimensions, 5, it's so abstract, right? But think that you are a person or an agent that has lived all its life in a 2D world, right? That your universe is 2D. And now you need to understand 3D rotations, right? It's like, how am I going to understand? It makes no sense, right? So the same problem, that's the same problem we face when we think about 4 dimensions. To us, it doesn't make any sense, right? But once you understand all this math, things make much more sense, right? They're actually easier to understand. Still hard, but they're much, much easier than otherwise. So this gives us now the DCT, or discrete cosine transform. Now, if you want to know, I'm not going to cover all the details of DCT. That would be like 3 weeks of lectures. And again, I don't know if signal processing does cover this in detail. But you will see that if you can just go out there and Google it, for example, right? Just out of curiosity, do it, right? And you will see there are 4, 5, or 6 different types of DCTs out there. And it depends how you actually defined all the details of the equations, right? Where you center them, which values that you take for the basis, and so on. The most typical that are used, the most typical DCT basis that you will see out there are DCT and DCT2. And they're defined as follows. Let A be an image, right, or a matrix. And let's say that our matrix or image is of m by n dimensions, right? M by n pixels if it's an image. Then the compressed tensor, then the compressed tensor is given by, let's see, PQ is equal to alpha I, alpha j, the sum over all I, let's say again from 0 to m minus 1 that I have been using, or used n, okay, let's say m. And, oh, I used m here, m and n right here, and j from 0 to n minus 1. Now the element aij, right, the ith row, jth column of my matrix times 2 cosines, right? To define the space, I need 2 cosine waves. The first cosine is going to be pi times 2i plus 1p divided by 2m, and all this times the cosine of pi 2j now plus 1 q. Should that be q? Yeah. Divided by 2n. And now here we need to vary p and q in our range, right, to go through the image, right, or through the matrix. So p has to be equal to, or has to go from 0 to what? M minus 1, right? And q from 0 to n minus 1, right? Make sense? Yep. Now, these are just constants. So we have alpha p is equal to 1 over the square root of m for p equal to 0, and the square root of 2 over m for p between 1 or let's say p larger than 0. Let's do just that. And alpha q is equal to 1 over the square root of n for q equal to 0, and 2n square root of 2n for q larger than 0. If you want to use this specific equation and parameters for the equation, in MATLAB, unless it's changed recently, use the function Dct2. So what you want to do is you want to get B, right? You want to get this basis, right, or this representation rather, B, which is going to be equal, right, to, is this a multiplication for your basis that we have defined here, right? So this is the tensor. So B dct 2a. You may need to specify m and n or not. Yep. And obviously, we can do the opposite, right? We can also write this down. We can also write this down as Aij is equal to, now the sum is going to be for P and Q, right? So P from 0 to m minus 1, and Q from 0 to n minus 1. And now I'm going to have alpha alpha P, all right? Yeah, alpha P. Okay, I don't know why I put this here. Shouldn't this be in here, right? That makes more sense. So alpha P, alpha Q, right? B, PQ, the cosine of, again, pi 2i plus 1 P divided by 2m, and times the cosine of pi 2j plus 1 q over 2n, right? So in other words, A, our image, can be written as a sum of these cosine waves, right? So if you want to implement this in MATLAB, I'm going to give you some hints. And then what we're going to do, so here's what we're going to do. There's probably going to be, we'll see, we're probably going to have one more homework. And then what I probably like to do, I'm going to have one, so we're going to do, we're going to do one homework. It will probably be the edge detector homework that I've been promising, right? And then we can probably do an optional homework that I always like to do at the very end, which we'll post probably later on, which could be probably implementation of JPEG or something like that, which will allow you to, it's completely optional, but it's for extra credit, and will allow you to boost your credit by, say, half a percentage point or something like that, right? Which, if you're always, it always happens, right? That you have made a lot of progress over the course, and you're just this 1/2 percentage point away from changing grades, right? Those optional homeworks are very useful for that. Okay. So if you don't do it, you can still get a perfect score. But if you do it, you can then have a minor lapse in one of the other homeworks or midterms or final. So image compression. And I'm going to talk about JPEG in particular, which uses the Dct Basis. And I'm only going to sketch the solution here, so you have some research to do in your homework. So A is going to be, as we've defined here. Where did I define this? Here. This is your image, right? So A, it's your image. So you start with A. Let's define this as your image. Now you need to compute the you need to create an image that has enough precision. So you want to use a MATLAB function that is called aim_double A. Now these things might have changed in the last year or two since I prepared these lectures. So check, obviously, the details of the latest version of MATLAB. And then you want to get your Dct matrix. So JPEG in particular, what it does, it takes the image A and it divides that image into blocks, okay, or windows if you prefer. And each of these windows, it's typically of 8 by 8, right? So you can compute the Dct in MATLAB of a matrix. So I believe it's Dct MTX. And you specify the size of that matrix, so 8 for JPEG. And now your Dct basis is going to be given by T prime, or yeah. Okay, but before I say this, you're going to need, if you don't, I'm just giving you some information about how MATLAB works. There is a function, again, unless it's changed, that allows you to construct a block structure like this, okay? And you need to do add, not partial derivative, but add, there we go, block structure. And now T, and again, block structure T prime. Now, to do this product, right, to get this product that you need to get, you want to do a matrix product or a block product, right? And there's a function that is called block product, or maybe something like that. And you take your image, you indicate that it's 8 by 8, and you give it your Dct. Okay? You're going to need a mask. I'm not going to reveal what that is, but just to let you know that you need to find out that there is a mask that you need to apply. And with that, you can get your image into Dct space. And then to reconstruct, you will need to use the block product of your basis. this, once you apply your mask, let's call this B2, your B2 basis. So B2, 8 by 8, and you're going to need here something else, okay? Which is the invariant. Okay, I'll give you that information on this. The invariant, right, that we have seen here of the DCT. The invariant, the inverse, excuse me. I don't have a good day. Huh? And then once you've reconstruct this, this image, you can do im show, right, as always, of this. And that will show you the reconstructed. Okay? So I've given you here a sketch of what you need to do if you want to do this optional extra credit homework. But there are some details that are missing, right? And some functions that you really need to find how to work or how they're called. Okay? All right. Any questions? So let me go to the slides for a second. All right. So this is basically the DCT bases, or a subset of the DCT bases that are used, right? These are the cosine waves that define the tensors that we use to represent our functional space, right? And with that, we can represent any image with just the coefficients, right? And that's what we're doing here. So that's the goal. It's very nice, and it's very easy and very nice to do that in your implementation of JPEG to actually plot the bases that you're using, right? So that you know that you're doing the right thing. There are multiple ways of scanning the image. You can scan the image as you want. This is the classical JPEG. But if you want to scan it like this, in that direction, that's fine. It doesn't matter as long as you only visit one of these 8 by 8 blocks once, right? You're fine. Now, the more DCT bases that you use, the more quality you're going to get. And that's what you see in JPEG of low quality, right? Probably not these days, but in my days, that's what we used to see. And or these days, you're watching Netflix, right? And the connection is really bad for a while. And you see these squares appearing in the image. That's the compression that you're using, right? The block size. You can actually see the block size of the compression that it's being used. And then, of course, if you don't get all the coefficients, you just get an average, say, for each block, right? And then you get something like this. It looks bad, but it's still, I mean, you can tell what the image is, but you don't obviously get all the coefficients, so you don't get all the details. And here you have an example of an image, and if you zoom in, this is what you would see with high compression, right? You can see the squares. You see them here, right? But you can get more and more DCT bases, right? And get better and better definition. So it's all a matter of how many coefficients and how many computations am I willing to send, right? And that determines the size of your files, of the information you need to send through the network, and so on and so forth. Okay? All right, any questions about this? So I want to turn now to another application of the DCT basis, which is for non-rigid structure from motion. Now, remember that we talked quite a bit early on matrix factorization and specifically for structure from motion, right? But one of the assumptions that we had to make in order to solve the equations was to assume that the object or the scene that we're modeling is rigid, right? That it never changes. Now, of course, this is very unrealistic because most objects move and deformed. So how are we going to address this? Let's look at an extreme case. Say a person like this. This is a video of an American Sign Language speaking in sign language. And you can see the different facial expressions, right? Now let's assume that these point correspondences that we need are already given to us, right? If you're interested on how to get this, computer vision and machine learning are the courses that you want to take. These are points that are obtained completely automatically, right? But you need to do this accurately across a video sequence. You need more than the template matching that we saw here in class, right? It's much more complicated than that. But given that, given this set of point correspondences, now here's what we need to solve for. We need to determine the position of the camera with respect to the object, right? So we either recover the translation and rotation of the object or of the camera, right? Let's say the camera, because this is a deformable object, so it's easier to define the camera position, okay? So instead of assuming that the object moves, I assume that it's the camera that moves. It doesn't matter, right? One or the other. Okay. So for this video, these are the cameras, right, that correspond to each of the frames, okay? And so that's the first thing that we need to recover. Now we need to recover the structure of the object, but the structure of the object for each frame is different, right? So the number of parameters that I have, remember before, the number of parameters for the object was fixed throughout the video sequence. Now it's different for every frame, okay? So we're going to end up, we're going to do derivations on the board now, but we're going to end up with more unknowns than equations, many more unknowns than equations, right? This is what's called an under constraint problem, right? So it's the opposite of where we use least squares. That's an over constraint, right? Doesn't have a solution, so we find the one that minimizes the least squares error. Here, the problem is there is no solution. Well, there is an infinite number of solutions. There are plenty of solutions. Just can't choose any because there are infinite of them. How am I ever going to know? All right, so that's what I want to show you, how you can use the Dct basis to actually solve this problem. Okay, so we're going to use compression, basically. Whoa, what the hell happened? Okay, why is that? We keep having technical problems, recently. Okay, let's see if that works, and if not, I'll try again. That's very odd. I don't know if I'm erasing everything or not. Can't see a thing. This one went off. Why is that one still on? Okay. All right, I'll have to write on this side if that doesn't go away. Let's see. Okay. It's off now? Okay. All right. So look, I erased everything. It's amazing. So this is non-rigid structure from motion. And you will see generally this abbreviated NSfM. Okay. So remember, we have a video sequence. Which is a number of frames, right? And for each frame, I have a shape, Si, Sj, so on, right? Or S1 through Sn. And now the trick that we're going to use is that we want to represent the shapes in some Hilbert space, right? So what I'm going to do, I'm going to find some basis vectors that are going to define my shape space. Now these shape basis vectors, right, are generally referred to as the basis shapes. So the shape space is given by the basis shapes. You see how this works? Instead of basis vectors, we call them basis shapes, right? Or basis functions, basis shapes. So here, right, and I have this basis shapes that define my so let me call this, let's see, I'll call this, I don't want to make this more confusing than it's needed, S1 through Sn, say the number of frames, capital S, that is. And now let me call the basis shapes a small s, so we'll call them S1, S2, Sj in general, okay? So I'm going to use capital S I for the ith shape and a small Sj for the basis, okay? So I have a specific capital Si, a shape, right? In the ith frame or at time I. It's going to be equal to the sum of j from 1 through, say, k, capital K, that is, of Cij, Sj, right? You see how this works? And this Sj, let me do that. This Sj are the basis shapes that define my space, right? And in that way, I can now represent my shapes using these coefficients right here, right? These are the coefficients that define my shape. So, in other words, I have in my shape space here, I may have, say, an object that looks something like this, and the slides, of course, have a better drawing of that, right? Say an object that looks like this, and that object is represented by this feature vector, right, that has coefficients, say, C1 through C capital K, right? Right here. Now, if I deform that object, right, that object, you see, is wider than taller, for example. So maybe I'm going to make it even wider. I'm going to extend it, stretch it in that direction. And that means that this coefficient has moved now here, right? So maybe I can call this, to make it simpler, I'll call this the vector of coefficient C1 vector. This may be C2 vector, right? And maybe now I deform the object in this way, for example, and that corresponds to a C3 coefficient vector here, and so on, right? I can keep deforming the object. But the important thing that I want you to realize is that as I deform an object, that corresponds to moving my vector of coefficients, right? Moving it in my shape space. You see that? So when I deform an object, that defines a function, right? A curve in that shape space. Yep. So let's go back to the definition of structure from motion that we had. Now, in a structure from motion, we had our observation matrix, W. What was W, the observation matrix? It has the point correspondences, right? So it has the U's and V's of the fiducial points that I'm tracking over the video sequence, right? So, for example, I have, for the first point in the first image, U11, V11, right? And so on, up to, say, UT1, VT1, and U21, V21, I'm sorry, not 1, 2, 1, 2, did I say that right? Yes, 1, 2, and UT2, VT2, right? And now here it's going to be 1n, 1n, tn, tn, right? So that's my observation matrix, right? Or my data matrix that has all the points tracked, right, throughout the video sequence. And let's see. What I have is my W is equal to my rotation matrix times my other matrix of, okay, let me do this instead. My rotation matrix, which has, or transformation matrix, let me do everything together. It has the rotation and the translation. So R2, T2, RT, TT, right? So this defines the movement of the camera. Oops. Okay, that should be T now. Okay, that should be T. I'm using T here, and N for the number of points. So that defines the movement of the translation and the rotation of the camera, right, at each point. Okay, now I'm going to add maybe a hat here, because in this class, thus far, we have talked about the affine model, right? So in the affine model, remember that this is a 2D rotation and translation, right? And then I have another matrix here, right? This is the transformation matrix, rotation and translation. And I have another matrix here, which is the shape of the object. So this would be, for the first point, capital X1. This is capital X, just to distinguish them, or small x, it doesn't matter, because I use UMVs, right? Yeah, okay. So Y1 and Z1, right? So this is the first point that I track, right, of the endpoints that I have in 3D space, right? And X2, Y2, Z2, all the way to Xn, Yn, Zn, right? Okay, so that was for structure from motion, meaning rigid structure from motion. Now let's extend this to non-rigid For the non-rigid model, I'm going to write, let's see, I have my U11, V11, and I track this point. I'm sorry, this is for the first image. So U11, V11, and then U1n, V1n, right? So these are the n points in the first image, right? And that has to be equal to my rotation matrix times my shape. How is my shape defined now? My shape is defined like this, right? Right here. So I have the sum, right, of j from 1 through capital K of C1 j S j, right? Small s plus t, correct? Okay, so this would be R sub 1. And now let's put this together. So I have W, right? Again, my matrix of observations here is going to be equal to R1 hat all the way to RT hat. Now, times. Let's see how this works. I open parentheses. Now, I need to have my coefficients here, right? That's going to be a matrix of coefficients. So let me write this matrix of coefficients. It's going to be C11 through C1 capital K, CT1, CTK. I'm going to leave some space here for a second. And now here I'm going to have my S1, S2, SK basis shapes. See how this works? Okay. Now I cannot multiply this directly, right? But I can use the Kronecker product here with I3, where I3 it's the identity matrix of 3 dimensions. Now remember, that I define this product here as, say, A connected product with B is going to be equal to, I multiply every element of A with the matrix B, right? So I do A11B all the way to A1NB. And in this direction, let's say I have T again, right? T1, B, A, T, N, B, right? So what does this mean? That means that now I convert this into a matrix of the size of this one, and I can do the multiplication, right? Now, these basis vectors, obviously, the reason I did this, these basis vectors are in 3 space, right? Or 3K space, rather, I should say, because I have K. Well, in that case, all right, let me put it here. In this case, this is 3K, right? The number of bases that I have. And remember that our R's are 2 rows by 3, right? Columns, okay, because they are affine. So let me write this probably in a more compact form. I can probably write this more compactly, like W is equal to D C the Kronecker product with I3 times capital S. I'm going to call capital S this, obviously. This I3. This I'm going to call it C, right? Plus T and T I'm going to multiply by a vector of all ones. Okay? This is a vector of all ones. So D here, just to clarify, should be a matrix that is of T by T, no, T by N, rather. No, it's 2T. Hold on, I'm lost. D, it's this one, right? So it's 2T by 3T, right? Am I right? What do I have? C, this one. This is T by K. And S is, again, 3K by N, right? Right? That has to be by N. Okay, because I have N points. Right? Okay, so my unknowns. What are my unknowns? My unknowns are, where is here? My unknowns are the rotations, right? The transformation, basically, and my matrix of coefficients, right? That's a problem, right? I mean, the number of equations is never going to be as large as the number of unknowns in that single matrix. This has T by K unknowns. It's absurd, right? So this is unsolvable like that. So what we need to do is R is fine. We don't care about R. But we need to represent C, the matrix of coefficients, in a compact way. And what we're going to do is we're going to take advantage of that fact that I just pointed out earlier, that the coefficients define a function in shape space, right? And that function is nothing else than a curve. That function can be represented as a set of basis functions, right? And I'm going to use the Dct basis to describe this function space, okay? And by controlling the number of Dct bases that I use, I can reduce the number of unknowns tremendously, right? So let's do the derivations of that. So I'm going to use the Dct basis. Let's call it omega d. Okay, I'm going to get the new one because that doesn't really work. Okay. So I'm going to use the Dct basis omega d. With omega d, I'm going to define it as the real domain of T, a matrix of T by D, right? T is still the number of frames, and D now the number of bases that I want to use to describe these functions. So I'm going to have C, the matrix of coefficients, equals to that matrix omega d times x some new coefficients that I need to determine with capital X, the matrix of D by K. Okay? All right, let me call this thing that I have here M, okay? That's D times C connected product with I3. Now, this D C I3 will be D omega D capital X product with I3, right? You agree? I only substituted C. And now we need to solve for X, okay, to get my M. Remember, I'm going to call this M, okay? To get my M, I need to solve for X. Now, how do I do this? I'm going to use nonlinear least squares, which means I need to initialize X with a value. A good choice is just to put the identity matrix in the first columns and then zeros for the remaining of the columns. And now to use nonlinear least squares, I need the initialization point, this one, and I need to differentiate the M, right? My matrix here, the M. So let's differentiate that, see what we get. So I'm going to get, let's see, this is equal to D omega D product I3 times differential of X product with I3 again. And let me call this term right here B, right? So I have B times D of X product with I3. Excellent. Okay. Now, to use nonlinear least squares, I need this to be a vector. It's not a vector, so let me say vect D of X. It's a function that maps this matrix into a vector, as we've done before, by taking the first row and putting it as the first elements of my vector, the second row, the following elements, the third, and so on. Right? And now we can compute the update over that new vector that I have by using the Jacobian matrix, right? So now we can update with the Jacobian. And the Jacobian matrix, the jth entry of the Jacobian matrix, if you redo the computations that we've done 100 times by now, is S sub j. This is the basis vector, S sub j, small s, times capital Pj and capital pi j, b capital V. And now these parameters that, or these matrices rather, that you have here, we have derived them before. This comes from the column space fitting algorithm, or CSF algorithm, that we derive for structure from motion. Okay. Remember that? And if not, do go back to your notes or the videos, right? But we derived all these parameters that allow us to compute the Jacobian back then. And V here is equal to IK product with Q, I'll call it 3D, product with I3, and ID product with my vector, I3. Missing one, don't I? With Q3D, a matrix 3D by 3D that is called a permutation matrix. Now, permutation matrix is nothing else than the identity matrix. Okay? Take the identity matrix, columns of ones, zeros everywhere else. And now we are going to permute the rows of this identity matrix. We're going to exchange them, right? Such as that the element 1 is now mapped to, who knows, element I, right? And the second element to J, and so on, right? And there's a permutation of the elements, and that is what will allow you to actually compute the Jacobian matrix. All right. Let's see then. Can I put the screen on? Yep. Okay. All right, so let's see a summary of this and a few examples. So again, this is the fiducial points that we are going to detect, for example, for that object, for a face. We need to recover the position of all the cameras and the 3D reconstruction for every single frame, okay? This is what the derivations I have done here in class. I call these small x and y's here instead of u's and v's, and this capital X, Y, and Z, same thing, right? And this is the rotation translation. So this is the classical structure from motion algorithm that we have seen in class, okay? And remember that was given the solution by this singular value decomposition, right? This least square solution. Now, the one that we've derived here today is the following. This is the observation matrix, which is this W matrix here, right? And now I have the matrix of coefficients for my shape space that is given by these basis vectors, right? And that means that if I have that object I was trying to draw on the board, right? So at every instant in time, meaning each of these columns now are the coefficients of that shape in that shape space, right? So this first row right here represents this point right here, these coefficients, right? And the second row corresponds to the second one, and all the way through all the points up to the last one, okay? That's how this works. Now, these are too many coefficients for me to estimate. So what I'm going to do, I'm going to use the Dct basis instead here, and then have these new coefficients x to determine how these other coefficients are given, right? Okay, how are we doing on time? I don't have time for this. I'll briefly talk about extensions of this model very briefly. The extensions of this model are not in the exam, just to make it clear. I'll cover this briefly in our next lecture. But let me jump ahead and maybe, oh, that doesn't work, does it? Let me try this. Let me probably show you a few examples. OK, so here's a, why isn't it? OK, here is the point tracking that we were talking about, right? And OK, this is another example, and this is the reconstruction that you, that you're going to obtain down here. You see how this works? Isn't that cool? You can actually recover the 3D shape of the object as it deforms in real time. I'm real time, not in real. Well, you can make this out and work in real time. Okay, and this is the reconstruction. So let me tell you what this is. So you take the first frame of that video here, okay, the texture of this frame, and you map it on top of this reconstruction, and now you get this. Now note that the mouth has some residual information because obviously that's the first frame that you're using. You're only using the first frame. But you can reconstruct the motion of the face and the texture even just from a single frame. And it's pretty cool. For this one, this is for an extension I'm going to mention on our next lecture. You will see that the space of the coefficients that can be reduced with this method can be reduced to just two coefficients, just two. These two coefficients define the shape of this face, and this is the trajectory of the shape in that shape, this reduced shape space. Extraordinary how much compression you can get out of this. That's why it's solvable, right? Because you can do that. This is the trajectory for a slinky as it deforms. This is for a shark. This is computer graphics shark that moves in a very circular manner. This is a walking sequence, and so on. But I'll talk about this. So one of the main problems that I want to briefly mention in our next lecture is that selecting the Dct basis is not easy, right? It depends on the problem. So when we derive this algorithm, this is, by the way, work done by one of my former students, who, as you will not be surprised by, after doing all this, was hired by Disney Research. And he's been there ever since. He seems very happy. But you see what they do in movies and in computer graphics for games or what have you, right? They have to model all these things, and that's the algorithms that they use. But at any rate, what was I going to say? I lost my train of thought. What was I? Oh, yeah. So what I want to say, the selection of the Dct basis, right? So when we were first deriving these algorithms, we applied this to faces, like what I showed you here. And the eye blinks that you saw in that video, they were gone. They disappeared. Why? Because we use a range of the Dct basis that eliminated the high frequencies, right? We only kept the mid frequencies, not the very low, not the very high. And eye blinks are high frequencies, right? So you actually get rid of that. But there is a way that we found out to solve this problem, right? I'll talk briefly about this and other extensions. The selection of the Dct basis is not a trivial problem. I don't want to make it look like this is, just out of the box, you plug it in and it works. You have to understand how these algorithms work to make them work in your problem, right? But if you understand how they work and you can make them work in your problem, they are extremely powerful algorithms. All right. I'll see you Thursday then.